stopped in the previous lecture. We started talking about solving these groundwater problems with increasing levels of complexity. So first we started off with the Laplace equation, where we solved just a steady state problem with no sources and sinks in a confined aquifer. The next thing we did was we solved the Poisson's equation, where you have one source or sink. In the specific example that we solved, we looked at spatial recharge over the entire aquifer, and then we set up the equation to solve the Poisson's equation. And then we looked at a numerical approach, the successive over relaxation method. We will move on from there now. Now we're going to add another level of complexity into the model. So let us say I want to incorporate a pumping well in my model. Okay. Now I'm going to think of the simplest possible example of incorporating a pumping well. So let us try and understand how to handle that scenario. Then we'll come back and figure out what to do, or you can imagine how to solve it if you want to do more complicated stuff. Okay. So let us imagine a domain that looks like this. Okay, some kind of a rectangular domain. Let us assume that the head at all of these four boundaries is all prescribed, or it's known. Okay, maybe the boundary condition could be a no flow boundary condition at all four, or it could be a prescribed head boundary condition. Whatever it is, the boundary conditions BC1, BC1, BC2, BC3, and BC4. Some boundary conditions are known at all the four boundaries of this particular domain. Okay, and I'm going to place a well right in the middle of this domain, okay, which is pumping at some rate Q. Okay, now let us assume that this particular aquifer is homogeneous, isotropic. Okay, so there's nothing, no directionality, no change in parameter in space or with direction. Okay, so I have this simple setup. Okay, now the question is, this is the domain in which this particular problem has been set up. The question that immediately arises is how to convert this into a numerical problem, and how to minimize the size of your numerical problem. Okay, is there a way in which we can make this particular problem, or is there a way in which we can solve this problem in a way that makes the entire problem, the solution of the problem, as simple as possible? Okay, so that's the question. Now, clearly, if I have a homogeneous isotropic aquifer, when I start pumping, I will create a drawdown cone, right, which will be symmetric in all directions. Okay, so let's say I have some kind of head contours in the area surrounding the well. This will be perfect circles. Okay, so I'll have this kind of a head distribution in the area around the well. I know this is what the answer is going to look like, right? Irrespective of what the pumping rate Q is, whatever the pumping rate is, this is what the solution will look like, right? Irrespective of what the exact value of my hydraulic conductivity is, it could be 5 meters per day, it could be 10 meters per day, whatever that number is, whatever K is, whatever Q is, the answer is going to look like this, right? I'm going to have head contours, which, well, let's assume that prior to pumping, it was the head is just uniform everywhere. There was no gradient. Okay, so a perfect Theiss solution, you can expect the answer. Okay, of course, you have an analytical expression to obtain the drawdown at any particular point using our Theiss solution. But suppose I want to compare my numerical solution and see if it matches well with the Theiss solution. Let's say that is my objective. Okay, I want to get a numerical solution using a numerical model, and then I have Theiss solution, which is an analytical expression, right, which you can easily solve by hand. Then my objective, let us say, it is to take this numerical solution and compare it with my Theiss solution. If that is my objective, then how do I go about setting up this numerical solution? Is there a way in which I can reduce the dimensionality of the problem given the particular system that I've set up? Any thoughts? Any thoughts on how we can solve this problem in as simple a way as possible? Let me give you a clue. The simplest way is to break down this entire domain into n number of cells in the x direction and some other m number of cells in the y direction, and then just solve it, right? Like usual. And our what is that? Our governing equation would look like this: dou square h by dou x square plus dou square h by dou y square plus q divided by t equal to 0. Let's say this is the equation that I'm trying to solve. Wait a second. Let us check if my units are consistent. What are the dimensions of the first term? It will be length divided by length square. So that's L minus 1. This will also be length divided by length square. That will also be L minus 1. Q is L cube T minus 1. And T, which is transmissivity, is L square T minus 1. So I have L cube T minus 1 divided by L square T minus 1. That gives me L in the numerator. So I have to divide it by the area of the cell. Okay, so if I break up this domain into different cells, each cell will have an area. So that area I'll use. So this is the area of the cell is the term that's over here. A. It's the area of the cell. So now I have q square, which is L cube T minus 1. The denominator will have L power 4 T minus 1. So then I get L minus 1 as the dimensions of this particular, then this equation is dimensionally homogeneous. Okay, this is how I would solve this equation if I were to apply brute force. Just break it up into n number of cells in x direction, m number of cells in in the y direction, and solve it. This is the equation I would solve. I know how to solve this. But can I make this problem simpler? That's the question. Any idea? How to simplify this problem? Can we use symmetry to simplify this problem? That's the clue. Can we use symmetry to simplify this problem? Okay, so let me say it like this. If let's say the drawdown in this particular circle, which is at a radial distance of some, let's say 10 meters or 20 meters from the pumping well, the drawdown at that contour that I've drawn is the same irrespective of which direction I move from the well. Whether I move 20 meters in this direction or 20 meters in this direction or 20 meters in this direction, 20 meters in any direction, the drawdown is the same. To get the same number, do I have to go in all four directions and all 360 degrees to find the answer? If I find it in one angle, then I can just at any one distance or at any one direction, then by symmetry I know the answer in all the remaining directions, right? We can do that. We can exploit the symmetry of the problem. What I can do is, okay, I'll reveal the answer. I'll break up the domain into 1/4. Okay. The original domain is of size, let's say this dimension is Lx and this dimension is Ly. Then I simply break up this domain into Lx by 2 and Ly by 2, and I solve only that first quadrant, right? What do I do after that? That first quadrant, I take the mirror image, that gives me the answer in the second quadrant. Second quadrant's answer, I take the mirror image into the third quadrant, that gives me the answer in the third quadrant. And then the third quadrant's mirror image will give me the fourth quadrant's mirror answer. Or if you want to do it even more simply, first quadrant, take the mirror image, you get the second quadrant, take this mirror image of the first and second quadrants together, that gives me the answer in the third and fourth quadrants. Does that make sense? So instead of solving a problem of size Lx by Ly, I'm solving a problem of size Lx by 2 into Ly by 2. Is that not numerically a smarter way of solving it? Of course, I have to clarify one point. The boundary conditions are the same in these whatever boundary condition 1, 2, 3, 4. Either all of them have to be no flow boundaries, or all of them have to be constant head boundaries of the same value, whatever initial constant head is there. Okay, if that is the case, then I can use this. I can use symmetry to break down this problem into 1/4 of the original size of the problem. The original size of the problem is Lx by Ly. I break it down into Lx by 2 into Ly by 2. That's 1/4 of Lx into Ly. So that's a smart way of handling this type of situation. But now, when I break it down into the smaller domain, the equation that I'm solving, the way in which I'm solving it will not be exactly the same as how I would solve it if it was the entire domain. If I was solving the entire domain, I know how to do it. Okay. But if I'm solving it for 1/4 of the domain, I have to be a little bit careful because I have created two new boundaries. This original boundary is the same as the boundary that I had for the original problem. This boundary also same as whatever I had for the original problem. But now I have produced these two new boundaries, these dotted lines, for which I don't know how to solve. Or these two new boundaries have been created by me in the process of trying to solve this problem. Right? In the process of simplifying this problem, I have created two new boundaries at which I don't know the boundary conditions. So I have to be a little bit careful. I have to be a little bit thoughtful about how I handle those two new boundaries. Okay, so we will just try to discuss how to solve those two boundaries. Okay, let's just imagine that now I'm solving this 1/4. Okay, let's say I break it up into some number of cells in the x direction, and then some number of cells in the y direction. Okay, and remember the well is in this, the pumping well is in that cell. That corner cell has got the pumping well, and then I have the remaining cells. Okay, so now if I pick any random cell in the middle of this domain, my usual procedure, if I pick any random cell in the middle of this domain, I know how to write this equation, right? The governing equation, dou square h by dou x square plus dou square h by dou y square plus q divided by a into t equal to 0. Right? Now remember, this q is only in that middle cell. It's not in every cell. This pumping well is only in the middle. It's not present in every cell. For all other cells, q is 0 because there's no pumping well in the other. Apart from this one cell in the corner, none of the other cells in the model have any pumping well. All the other cells, that q is equal to 0 basically. So basically, for all other cells, the equation will be dou square h by dou x square plus dou square h by dou y square equal to 0. This will be the equation for all the other cells, which of course we have already written the format for this: I plus 1 comma j plus I minus 1 comma j, I comma j plus 1, I comma j minus 1 minus 4 h I comma j equal to 0. Right? So this is This is the equation that I can solve for all the other cells. Very easy, straightforward, right? So I know what to do. So this is for a random cell in the middle of the domain. Now let us look at, let us say I pick this particular cell. One cell which is on this boundary. Now remember that this boundary did not exist before. In the original problem domain, this boundary, this was not a boundary. This was a cell in the middle of the domain, right? So therefore, whatever you could have done in this original problem domain, you can't do for this new domain, because this new cell is a boundary which did not exist before. Okay, now the same equation applies to this cell also, but you will notice that there is only an I plus 1 term. There is no I minus 1. For this cell, if this is, let's say this is I equal to 1, so in this equation, I plus 1 will be this next cell. But what about I minus 1? Is there a I minus 1 cell here? We are on the boundary, and this boundary is an artificial boundary. It didn't exist before. So what do we do with that I minus 1 cell? Anybody? Does the I minus 1 cell exist or does it not exist? So let's call this cell cell 1. Okay, for cell number 1. For cell 1, H I plus 1 comma j. This I minus 1 comma j doesn't exist. Okay, I'm going to leave it blank for now. Plus H I comma j plus 1 plus H I comma j minus 1 equal to 4H I comma j. Okay. Now this I minus 1 cell exists in reality, but in this new model that I've created, there is no I minus 1 cell. There is no cell here. But by symmetry, can I say that this I minus 1 cell head must be the same as the head in I plus 1 cell? This boundary, there's one cell to its right, another imaginary cell to its left, which doesn't exist. Does everybody agree with that? How to handle the cell along this first column where there is no I minus 1. This I minus 1, this imaginary I minus 1 cell. Okay, so if I were to write it like this. This is I, this is I plus 1, and this I minus 1 cell is imaginary. But if that cell existed, the head in that cell will be the same as the cell, same as the head in I plus 1 cell. Does everybody agree with that?
Yes, sir.
Anybody else? Vicky, you agree with that?
Yes, sir.
Okay, very good. So in that case, if this, remember this I minus 1 cell doesn't exist, but to include it in the model, I'll have to simply do 2 times Hi plus 1 comma j, because I minus 1 cell would have been equal to I plus 1 cell head. So now I have figured out how to handle that particular cell, and I'll have to do this for all the cells in that column. I'll have to do this for every cell here. I'll have to do it, right? So I've shown you how to handle one particular cell in that in that column of cells. You will have to do the same thing for every cell in that. Okay, we'll come to the last, the pumping cell also. That's the last thing to do. Okay, now similarly, if you take any cell in this boundary, again this boundary also didn't exist before. Now let's call this cell 2. This is cell of type 2. Okay, so for cell 2, what will I do? I'll do something similar. It has an I plus 1, it has an I minus 1. what it doesn't have is a j plus 1. It has a j minus 1, but it doesn't have a j plus 1 cell. There is no cell here. Now, cell in the j plus 1th row doesn't exist. So when I come to that, I will write it like this: h I plus 1 comma j plus h I minus 1 comma j. Now these two exist. I plus 1 and I minus 1 exist. No problem. Plus 2 times h I comma j minus 1 equal to 4 times h I comma j. Is that all right? So now in this case, I have,
Sir,
yes, go
instead
ahead.
of 2hi j minus 1, I can also read 2hi j plus 1.
But j plus 1 doesn't exist, Vicky.
But you call that you can put at same I minus
No,
1 I.
no. See, remember this, whatever equation I've written is only valid for this last row of cells. This is only for, let's say this is j equal to 1, 2, 3, 4, all the way up to capital M. Okay, this is for j equal to M. Only for the row number j equal to M, you can write this equation. Because there is no M plus 1th row, j plus 1 doesn't exist. I say it must be equal to j minus 1, which is M minus 1. The previous row's values, you have to take it twice. For all the rows or for all the cells in that particular row where j equal to M. And this equation is, so if the cells go from I equal to 1 to up to n, this first equation that I wrote is only for those cells where I is equal to 1. Understood? When I equal to 1, I minus 1 doesn't exist. So I did 2 times h of I plus 1, which is row number, column number 2. Is that okay, Vicky?
Okay, sir. Okay.
Thank you. Okay, so in this cell, there is an I comma j and there is an I comma j minus 1, but there is no I comma j plus 1. This cell, I comma j plus 1 doesn't exist. But I know from symmetry, by the principle of symmetry, I know that the value in that must be the same as the value in the j minus 1th cell. And therefore, I simply write that equation, and that takes care of all the rows, all the cells in row number M. And a similar approach accounted for all the rows, all the cells in row number 1 or column number 1. Okay. Now, there is a special cell which is this corner cell, which is where the pumping well is. Now, this one neither has I minus 1 nor has j plus 1. Okay, so I'll just do that in the next. Okay, so I'll just draw that again. Here I have, I'll just exaggerate this a little bit. Okay, here I have a pumping well in this very corner cell. Okay, so now when you look at this particular cell for I equal to 1 and j equal to M, it's the last row, first column, this particular cell where my pumping pumping well is placed. I will get something of this type. Hold on a second. So the equation will no longer be this dou square h by dou x square plus dou square h by dou y square equal to 0. The governing equation will be this original equation that I wrote, dou square h by dou x square plus dou square h by dou y square plus q divided by a t equal to 0. That is the governing equation for that cell alone. Okay, because that q, that pumping well exists only in that well. In all other cells, pumping is 0. So you don't have to worry about that q term in all the other cells. But now when I come to this corner cell, I have to be a little bit careful. So it will be h I comma j. Wait a second. So it will be 2 times h I plus 1 comma j plus 2 times h I comma j minus 1 plus or minus, wait a second. Okay, I tried to skip steps and I end up. Let me not skip steps. We'll go step by step. Okay, let's remember what our equation is. Our equation has dou square h by dou x square plus dou square h by dou y square plus q by a t equal to 0. Now this dou square h by dou x square plus dou square h by dou y square, that term will have 2 times h I plus 1 comma j plus 2 times h I comma j minus 1 minus 4 h I comma j divided by delta x square plus q divided by a into t equal to 0. Right, so when I rearrange this, I will get h at I comma j. Okay, put this to the right hand side. Okay, it will be 2h I plus 1 comma j plus 2h I comma j minus 1 plus q into delta x square divided by a to t divided by 4. Have I done the algebra correctly? Yeah, I think it's okay. Right. So I've got all my I've got a different approach for each cell depending on what is going on in that particular cell. For any cell in the middle of the domain, I don't need all this. For any cell that's in the first column, I already explained what the approach will be in the previous slide. For any cell which is on the last row of my domain, I again explained that. There's a special row, there's a special cell which is at the corner of the first row and the the first column and the last row, which is the cell where my pumping well is also located. So for that particular cell alone, I have to handle it special. I have to have some special arrangement for that particular um, situation, right? And this is how I handle that. So I set up the equation, and what we end up with is an equation that accounts for all um, uh, the special circumstances of this particular cell. This particular corner cell neither has an I minus 1th cell nor has a j plus 1th cell, right? Because it is at the corner, right? So therefore, because it doesn't have I minus 1, I do 2 times h of I plus 1 comma j. That's the first term. And because I don't have a j plus 1 term, I simply do 2 times h I comma j minus 1, which is the previous row. Okay, and then the other next term is the taking care of the pumping term. Okay, the whole thing divided by 4. This gives me the head in the cell which is holding the pumping well. Now remember, again, when I solve this system of equations, I'm going to be using an iterative method, whatever Jacobi iteration or Gauss-Seidel iteration. I'll have to do that. If you want, you can do the successive over relaxation. All of that is still the same as before, right? No change from before. So this is how I handle the incorporation of an additional level of complexity, which is a point source or a point sink. That this pumping well could be pumping water in, or it could be an injection well or a pump out well. Right? It doesn't really matter. If it's pumping water out, then this Q will have a negative sign. If it's pumping water in, then Q will have a positive sign. Right? Of course, typically we imagine a pumping well, so which means I'm extracting water out. So therefore, this Q will have a negative sign. That's all. Right? Other than that, the method is the same. It really doesn't matter whether the well is pumping in or out. You'll just account for that by changing the sign of your Q. Okay. Yeah. Any questions? No questions. Okay. All right. So then let's move on. The final aspect that we are interested in looking at now is what to do if my problem is no longer a steady state problem, but it's a transient problem, right? So the transient problem, again, my governing equation will look something like this: dou square h by dou x square plus dou square h by dou y square plus w by t, some source or sink term, equal to s by t dou h by dou t. Now this is my governing equation for a generic transient problem. Now the source or sink also, I'm not specifying what type of source or sink it is. It could be recharge, which is aerially distributed, or it could be a point application like a pumping well or injection well, or it could be a river which is connected along a line, right, with the aquifer, and so on and so forth. So I'm not getting into the details of how specifically we handle different types of sources and sinks. That's for a higher level course. Generically speaking, if I have this kind of a setup, then I simply rearrange this. What will I do? I simply rearrange this as follows: dou square h by dou x square plus dou square h by dou y square equal to s by t dou h by dou t minus w by t. Okay. Now the left hand side that I have over here, that is going to be my standard formulation. Now we all already know how to handle this type of a setup. It will be h I plus 1 comma j plus h I minus 1 comma j plus h I comma j plus 1 plus h I comma j minus 1 minus 4h I comma j, the whole thing divided by delta x square. Remember, we are assuming that delta x is equal to delta y, more or less, plus or minus. So we are not really going to worry about that. Equal to, now we have to be a little bit careful here, s by t, s divided by t, h I comma j at, okay, let me not use t plus delta t. Let's use the time step. N plus 1 minus h I comma j at n divided by delta t minus w by t, whatever it is. Okay. So now when you look at this term, on the right hand side, I have the time derivative of head. So I have hij at n plus 1, which means n plus 1th time step. Remember, now when we solved the iterative problem, we used m to refer to iteration number. But remember, up to now, we were only looking at steady state problems. So that subscript or superscript of the iteration number was referring to a steady state problem, but where I'm solving iteration m, m plus 1, m plus 2, and so on. But now here I have the head itself is marching through time, right? I start at time t equal to 0, then first time step, second time step, third time step, and so on. So this n and n plus 1 refer to the time step, not to the iteration number. So that's something that we have to be careful with. Okay. So on the right hand side, I have this n plus 1 and n. What about all the terms that are on the left hand side? Again, I have I plus 1, I minus 1, j plus 1, j minus 1, and I comma j, right? All those terms are there. Should I refer to them, or should I, which time step should I refer to uh, for the terms on the left-hand side? And what does it mean? Should I use n plus 1? Should I use n? What should I do? Now remember, there is no correct answer for this question, right? There are two ways of solving it. One is to solve it as an explicit solution, in which case, when I say explicit solution, all the terms on the left hand side which are not connected to time, right, will all use the old values of the head, right? So here I will have n. These values will be computed at the nth time step. So when you look at this equation now, you will see that this equation has only one unknown, which is hij at n plus 1. Everything else, all the other terms have got, we've got the head values at different cells in the 5-point stencil: I comma j, I minus 1, I plus 1, j minus 1, j plus 1. For all those 5 neighboring cells, for all those 5 cells in this 5-point stencil, the values are known at time step n, right? Remember, whenever we are solving a transient problem, we require one initial condition. So if I know the initial condition at time t equal to 0, I can always solve for the first time step in this equation, which would be n plus 1. I can always solve for the head at the next time step. And once I solve for that in all the cells in my domain, then I can go to the next time step. At that time, I will know n and I don't know n plus 1. So in this equation, if you pay attention, you will notice that although I have so many different terms here, the only unknown is the head at the n plus 1 time step in that particular cell. All the other terms are known. So this is the what is called the explicit formulation. I'm not going to write the implicit formulation. You know what to do. Just replace n with n plus 1 on the left hand side, and when you do that, then the formulation becomes what is called the implicit formulation. The implicit formulation has some advantages. It has advantages of stability and so on, but it is more cumbersome to solve. The explicit solution is relatively easier to solve, in the sense that um, uh, 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 what you're solving in this equation, one equation, one unknown, easy to solve. Whereas implicit solution has got some complexities when it comes to solving the equation themselves. Okay, let me just try to set this up equation. Let us just move all the terms in such a way that I collect all the unknowns on one side, and which is I comma j at n plus 1, and all other terms will be moved to the right hand side. So if I do that, I will get something of this type. I'll try not to make a mistake while writing this. Hij at n plus 1th time step. I'll just write it. You don't worry about memorizing this or anything. I'm just writing this from the solution itself. 1 minus 4t delta t divided by s delta x square. This whole thing times h I comma j at the nth time step, plus 4t delta t divided by s delta x square into, this is I minus 1 comma j, I plus 1 comma j, I comma j minus 1, I comma j plus 1, whole thing divided by 4. Now all of these will be at the nth time step. Plus whatever times w delta t divided by s into a, something like that, area of the cell. Okay, so this would be the the explicit formulation of the transient problem. So this I can solve. I can set up as many equations as I want and solve each of them successively, because all of this only rely on the right hand side, completely relies on whatever was the head distribution in my entire domain at the previous time step. Whenever I come to a current time step, I already know the head in the previous time step. Only then I can come to the next time step, right? So everything on the right hand side is known. The only unknown is on the left hand side. So you just simply solve for it, go to the next cell, and then you can loop through all the different I comma j's, right? You go through it in a systematic way, in such a way that you always know I minus 1, j minus 1, I plus 1, j plus 1, whatever. Okay, everything is known. But like I said, although the explicit scheme has got advantages, it does have a stability requirement, right? It has a stability criteria. Let me just write that also. Okay, so the stability criterion is as follows: T delta T by S delta x square must be less than or equal to 1 by 4 for a 2D problem. And for a 1D problem, it should be T delta T by S into delta x square should be less than 1 by 2 for a 1D problem. Right, which is, if you look at that system, what that will tell you is, if this number is less than 1 by 4, then this term will be positive, right? If it is more than 1 by 4, then I'll get 1 minus some term that is greater than 1. Therefore, this term will become negative, right? And then that creates some kind of a problem, right? So in order for the solution to be stable, which means for the stability of the explicit scheme, I require these terms to satisfy this. For a 2D problem, it should be so and so, and for a 1D problem, it will be so and so on, right? So that is as far as we will talk about in the case of a transient problem. We are not going to have the time to discuss anything further than this, so we will stop with that. Now, just to give you a kind of a brief idea about how groundwater modeling works in practice in the field, right? What are the tools that people use most often, and so on and so forth. So the one of the most commonly used, or the most popularly used software around the world is what is called ModFlow, right? So it translates to modular flow, right? And this ModFlow software uses finite difference formulation. Of course, these days there are improved formulations, but fundamentally ModFlow, when it was first developed, was a finite difference based solution of the groundwater flow equation. Okay, and then something that's been used recent times is FE flow. Now this FE stands for finite element. Okay, so now this approach is also gaining popularity, and there are lots of people who are using FE flow to solve a lot of groundwater problems around the world. But ModFlow continues to be probably the most commonly used, most popularly used. But FE flow is also becoming very, very common these days, and a lot of organizations use FE flow. Now, when it comes to using ModFlow, there are many graphical user interfaces, what's called a GUI, GUI. Lots of GUIs are available, which you can use to set up a ModFlow model. Because ModFlow is kind of an old 1980s, it was developed. At that time, people were very popularly using Fortran codes, which which is basically a command line based communication with the software. So what people did was to develop a graphical user interface which allows us to communicate with the groundwater model in the background. Okay, so this GUI, lots of GUIs are available: groundwater vistas, GMS, visual ModFlow, so on and so forth, right? So that's what's available in the market. I've just listed a few of them. Now, what has come in recent years, in the last 3, 4, 5 years, is this tool called FlowPy, which is a Python-based implementation of ModFlow, and which is very powerful because it allows us to automate a lot of the entire procedure for running, creating and running groundwater model. So if you want to try different combinations of parameter values and so on and so forth, becomes very easy if it's implemented through Python. So in your code, you can just enter different values for different parameters and just run it automatically, and then you can save the results automatically and then compare, what is the impact of this parameter, what is, how does it impact the results, for example, and so on and so forth, right? So obviously these days everything is going the Python direction. So uh, similarly, Modflow is also going for this Python based kind of implementation, and that's again something that's I would suggest that if you're interested in pursuing groundwater and groundwater modeling further, FlowPy is kind of one of the tools that would really help you out, of course, along with other existing tools, which can really help you to make progress in terms of your ability to quickly create groundwater models and be able to, make a difference. Okay. All right. So I think we are kind of out of time. We will stop with that for now. We'll meet again tomorrow, right? Tomorrow at 9 a.m. I think, and then we'll continue from there. Okay. I'm assuming that you guys are all getting ready for Friday's, um, presentation. Please email me if you have questions. Hopefully it works out well. Let's see. Okay. Thank you very much. Take care and see you all tomorrow.